On behalf of BIC Magazine and our sponsor, Montrose Environmental, I'd like to welcome everyone to today's presentation on the future of fugitive emissions, tactics and technology to streamline your LDAR program. This is Robin Dupree from BIC Magazine. A few pointers regarding your webinar console. There is a Q&A box on your screen to text in questions anytime during the presentation. The Q&A portion will occur at the end. Please join us in live tweeting during the course of this event and share your thoughts with our Twitter audience. Use the hashtag Montrose Webinar and BIC Webinar. If you experience any technical problems, send a chat message to the organizer and it will be addressed as needed. And now I'd like to thank our sponsor, Montrose Environmental. Montrose knows that dealing with the logistics and implications of environmental issues is vital. With more than 1,700 employees in 70 locations, Montrose focuses on the future of environmental solutions with an integrated approach to design, engineering, and operations. They apply the latest technologies in practical ways to solve difficult environmental challenges today and prepare for what's coming tomorrow. From lab services to stack testing to regulatory compliance, Montrose helps clients blaze new trails. Go to montrose-env.com for more information. And now it's my pleasure to introduce you to today's presenters. Our first speaker is Peter Zemek, Senior Vice President for Montrose Environmental. He leads the Emerging Technologies team and has worked in the environmental field for over 30 years. The second speaker is David Berkowitz, Technical Director. He has more than 29 years of industry experience and currently is a Fenceline monitoring subject matter expert at Montrose. Tanya Jackson, Vice President, U.S. LDAR Division, brings over 9 years of experience in the environmental industry. She is a leader in the field, holding certifications in Method 21 and OGI thermography. And now I'd like to hand the mic over to Tanya.
Thank you, Robin. Thank you, everyone, for joining us here today. We're really excited to share a lot of new approaches and technologies with you. Many of you listening here today either have an internal company policy to voluntarily reduce fugitive emissions or you're required by regulatory requirements. Either way, it's our collective goals to reduce fugitive emissions. Keep your product in the pipe, resulting in improved air quality for our employees and surrounding communities. We effectively do this through fugitive emission programs. LDAR technicians provide field support for many fugitive emission programs, but these programs are often discussed and managed individually. We're presenting on a collaborative approach to obtain a broader perspective to reduce fugitive emissions. This is going to enable us to identify fugitive emission gaps, identify solutions while employing all of the latest technologies, and develop streamlined plans for execution that's more efficient, accurate, and cost-effective. So how are we going to do this? Today, my colleagues and I are going to discuss the progressive steps that can take place using a sample facility to coordinate a comprehensive fugitive emissions program. Traditional LDAR programs identify emissions from components using Method 21, which is a point-specific inspection at every component. We're going to call this the micro level. The alternative work practice method uses an OGI camera, optical gas imaging, to scan large areas at the equipment and component level, much faster. This is the next level. Fenceline programs identify emissions crossing the boundary of a facility, and we call this the macro level. Each method has its own strengths and weaknesses. Therefore, the combination of these services with new technologies is going to give us that comprehensive view of your emissions on site and allow for a more proactive approach to address your facility-wide problems. David Berkowitz, a Fenceline expert, will present this sample facility and how to implement traditional Fenceline. I will be discussing how to streamline the collaboration with your LDAR teams to get boots on the ground and take the best approach. And Peter Zemek will discuss emerging technologies available to support these programs. David?
Thank you, Tanya, and thanks to everybody who was able to join us today. So I'm going to kick it off here and just kind of have a little intro to passive tube Fenceline monitoring for those who are not already intimately involved. Those of you who are associated with petroleum refineries know all too well what I'm going to discuss here. But basically, EPA method 325A and 325B dictate the deployment and sampling and sample analysis of passive tubes for monitoring various pollutants at Fenceline. In the case of petroleum refineries, this would be benzene. It's a federal rule for petroleum refineries. It is being incorporated into consent decrees for various other industries, and it is also EPA's intention to put this monitoring requirement in for other industries as well. So what is it? So passive tubes are deployed at the boundary of a facility. They're deployed for a period of 14 days, and they passively sample pollutants, which are then analyzed by a laboratory and give an average 14-day concentration. This is, a pretty low-cost way to do, an efficient way to do sampling at the Fenceline. Provides an accurate value, but one of the drawbacks, or several drawbacks, are the lag time to get results, and there's it covers a large amount of time in which the wind conditions can be variable and operations are variable as well. So your result is going to be not very indicative of what's going on day to day. Tanya, if you could advance the slide, please. So you got your program running, you get an atypical result. What do you do now? First thing is done with a root cause analysis is to go through your operations logs, look at your loading operations. Were there any spills during this period? Was there any maintenance activities going on? And also keep in mind any usual suspects that might be, responsible for fugitive emissions, such as tanks or wastewater treatment plant or loading operations. So these things are all going to be kind of your first go at it. Next slide, please. So while you're doing that, it's a real efficient way to kind of get some more information is to engage the laboratory. They should be able to provide some additional information from the sample analysis that has already occurred. This slide shows an example gas chromatograph, mass spectrometry, total ion chromatogram. And I'm just going to point out some features of this image. And you can see I've labeled hydrocarbons on the left side, and you can see where there's a small peak of benzene and then a larger peak of toluene. This is kind of a mix of the various components that were in the air over that 14-day period, and their presence, absence, or relative amounts can tell you a little bit about where the source of these emissions came from. There's a bunch of other peaks in there, and from that, the laboratory can drill down and kind of give you IDs of these other peaks, and that would shed light potentially on some other components as well. If you go to the next slide, this chromatogram, you can kind of just see for comparison, you have a much larger benzene peak and a smaller toluene peak, and then your hydrocarbons are in a smaller ratio relative to the benzene as well. So this, you can kind of see where these particular chromatograms are different and can shed some light on variable conditions. Next slide, please. So another approach that can be taken is to deploy shorter duration sampling tools. These can be in the form of passive tubes, or canisters. Canisters are typically collected over 24 hours. Your passive tubes can be collected for variable durations. But let's just say you kind of drop back to maybe a 7-day passive tube sample, and you get 12 microgram per cubic meter. That's a little bit more granularity than you had before with your 14-day average. But with the canisters, you've got a 24-hour snapshot. And that'll provide, so like this example, it provides 7 data points, and then the average of those 7 data points might equal 12 microgram per cubic meter. These shorter periods in conjunction with wind conditions can provide some additional clues on where the source of emissions are coming from. And how do these particular items get here? They are typically done with, able to be deployed with boots on the ground. So next slide, please. Another important component is going to be your wind data. Where did that wind data come from? Did it come from 25 miles away at an airport, or is it on site? And on-site Met Station is going to give you much better information. 1-minute wind vector data provide real-time information about what's going on. And so you kind of couple that with the additional shorter-term measurements, really has a powerful ingredient in trying to pinpoint the source of ID. So all of these tools here, your first approach, can be efficiently addressed with your LDAR team. The LDAR team, boots on the ground, out there, kind of being directed to try to track these things down with all of these tools. And with that, I'm going to kick it back over to Tanya.
Thank you, David. So when a Fenceline manager would contact our LDAR teams, we are deployed for various reasons. Like David said, it may be to collect or deploy more sample tubes, canisters, or to provide the boots on the ground monitoring support and identify the exact location of a leak. We would recommend starting with an OGI survey. The OGI camera allows for the fastest and most accurate qualification of a leak by surveying broad areas, equipment, and components. You really want to think about this when you're doing these types of investigations. It's like finding a needle in a haystack. And instead, using the camera first as opposed to a Method 21 device would allow for that broad perspective. This image here is a perfect example of a component at heights that as a point source Method 21 inspection may take much longer to identify if the leak was coming from here during this type of investigation. So optical gas imaging cameras have many benefits as discussed on. They definitely are faster. Again, we can see a broad area at one time. It allows for identification of the exact leak source by visual identification. Sometimes we get what we call ghost leaks, where we think that we've identified it with a Method 21 device, but you're downwind of the actual leak. And so you're getting basically a false identification of where the leak's actually coming from because you're downwind. It allows for observing leaks without the need for scaffolding or man lift. So it provides a safer, faster identification. Finally, it allows for identification of the largest leaks fastest. So as much as we could reduce emissions by finding the leaks faster, that benefits all of us. The data collected from this site shows that while Method 21 found 60% of the leaks, it only accounted for 10% of the emissions. And that goes to support that while the OGI camera found only 32% of the leaks, it accounted for 90% of the volume of emissions. Each method and technology we're going to present today has a purpose and a place, and it's knowing when to use each of these. Now that the camera has identified a leak, we would use Method 21 to quantify it. So here's examples of various devices, either PIDs or FIDs, where we would be able to quantify using these lower detection instruments. And these are also not specific they can account for total VOCs. We are also able to utilize survey monitors for more compound specific using point source measurements. If you're in a high industrial area or a large facility, you may be unable to identify the leak. So where do we go from there? We're able to deploy more sophisticated technologies at this point to drill down to identify the problems. It's important to consider the degree of the problem and how much time and money you have to fix the problem. For high specificity, lower detection limits, we would bring in more advanced technologies, and Pete's going to discuss that now with you.
Thank you, Tanya. All right, today I'm going to talk to you about a little bit more of the more advanced technologies that we employ. Now, many times when you have a very large site or a site that essentially is very complex, meaning it might be next to another facility, or it might be on, say, the Houston Ship Channel or some other canal where chemical barges are moving through, it becomes quite complex to determine where emissions at your fence line are actually coming from. So some of the technologies that I'm going to talk to you about today is a Montrose triangulation platform. And of course, this is an agnostic platform that Montrose has developed that ingests any type of data from many different types of instruments, whether they be low-cost sensors, auto GCs or process GCs along the fence line, or in fact, temporary CEM systems, and even our flagship, which is called the Proton Transfer Reaction Time of Flight Mass Spectrometry Mobile Van Platform. And I'll talk about that in a few minutes. Next slide, please. All right, so most platform systems or triangulation systems generally work by detecting a plume and then using meteorological station and various GPS coordinates, and of course mapping to determine where the source of the emissions are coming from. So many times the more or the less advanced technologies that David has put forth and Tanya has put forth are very good and can quickly solve your problem and really assist an LDAR program. But sometimes you have to bring in some higher technology, and I'm going to talk about some of these higher technologies in a minute. So here we have the agnostic triangulation platform, and then I'm going to talk about some of the technologies that actually hook up to this platform to tell you where your problems are. Next slide, please. All right, so this is basically the HMI, or human machine interface, of the Montrose triangulation platform. This is essentially what the customer sees. Essentially, all the data gets sent up and encrypted into the cloud platform, and then the cloud sends it down to our secure servers. The algorithms are on the server, and then they send that data back in real time. The customer can log into an IP address with appropriate security, and then they can see what's going on in real time. Many of the technologies we're working with here are called high temporal resolution, which means that they update very quickly, meaning anywhere from a data point every half second to a data point every 5 minutes, sometimes 15 minutes if you're working with GCs. But obviously, the faster the update, the quicker you can determine where the triangulation is and locate the source of the problem. And this can be done over long distances, even quarters, if not half a mile distance. Next slide, please. So the way this platform works is it uses an advanced algebraic algorithm, geometric algebra. And essentially, whenever you get a hit on at least 2 sensors, or if you're using one sensor like the mobile platform, it can be moved to a separate area, and then also use the triangulation from that secondary plume analysis, and then it can very quickly determine where the source of the emissions are. We've tested this over many different types of compounds, over many different types of topographic areas, and we've had excellent results. Next slide, please. I'll talk a little bit about those now, some case studies. In this particular case study, we actually, this is a metropolitan area in downtown Denver, and essentially that green circle that you see down in the bottom right-hand corner is a Montrose facility located in Denver. and we deployed 2 PID sensors on the roof, located approximately 25 feet apart. And then we left them up there and used the triangulation platform to see if we can find any plumes that were floating around this metropolitan area. Now, the minute that the first sensor or whatever technology we're using actually finds a plume, it uses the GPS and meteorological data to try to figure out exactly where that emission point is coming from. And here, one sensor has picked it up. We can tell the distance that that plume has traveled, and that's because actually the concentration of the plume is actually a function of the distance. Obviously, the farther away the plume is, the more dilute the plume is. So with our algorithm, we can actually very quickly and pretty accurately determine the distance of a plume. But as soon as we get a secondary reading off a secondary sensor or analyzer, next slide please, you can see that very quickly we can determine within a pretty good area, probably within a few meters, some of our case studies have shown very easily within a few meters, that we found a location here of a fermentation pipe on the southeast corner of a microbrewery. So we actually did not know that microbrewery was there, and so I would call this a very successful test because we found a microbrewery very close to our office. So to me, that was a win. Next slide, please. All right, some of the other technologies I'm going to quickly talk about, of course, is the proton transfer time of flight mass spectrometer. Now, this is a mobile platform, and what you see here are some of the technologies that we employ on the van. So we don't always just use the PTR. We also use many other different types of technologies, and that's because the PTR is very good at many compounds, but say we're looking for straight alkanes, it's not really necessary to use such a sophisticated piece of equipment, and sometimes we'll employ other equipment while we focus on more difficult to measure or lower detection limit requirements for some of those compounds. Next slide, please. So this is what the mobile platform looks like. It's essentially a Sprinter, Mercedes Sprinter van type. It's very incognito. We do have magnetic logos on it, but they can be removed for if a company doesn't want to call attention to itself, or if you're moving through a community to try to map that area. Of course, you don't want to alarm anybody. But the van is in fact equipped with a GPS system and meteorological station and a snorkel for raising up higher above the van to get to various levels so you can read the ambient air. The van is also equipped, if you open up the back door, we can pull out various distances of either heated or unheated sample lines. And with a data point coming every half second to 1 second, you can very quickly use those heated lines or unheated lines as what we call kind of a bloodhound technique, and really follow a scent right up to the location where the source of emissions are coming from. So remember, we're talking about part per trillion, if not part per quadrillion levels for many of these compounds. So this is an extremely sensitive piece of equipment, but the beauty of it is that we can bounce this down the road at 55 miles an hour without any problems whatsoever. And I'm going to talk about some of those case studies now. Next slide, please. So how does this PTR work? Well, it's actually very sophisticated, but actually very simplistic in its operation. In fact, what we do is we use a reagent gas, and there's many different types of reagent gases that you can use, and we choose the reagent gas based upon the target compound or compounds that we're interested in. We choose a reagent gas that has what's called a proton affinity that is less than the target compound, which means that if you have a hydrogen proton with a molecule, 2 molecules that have different proton affinities, the hydrogen proton is going to want to be with the molecule that has a higher affinity. So what we do is we introduce the reagent gas into a hollow cathode tube. It is then ionized. It is introduced with the sample gas, whether that be ambient air, and then the reagent gas reacts with the target compound and transfers a hydrogen proton to the target molecule, which in fact increases its atomic mass by 1 atomic mass unit. Now, the time of flight mass spectrometer is a high resolution system, so we can actually see down to the 0.1 atomic mass unit. and we can actually cover atomic mass units from 40 to 4,000 atomic mass units. So very sophisticated piece of equipment, actually very ruggedized too. We have not had any problems bouncing this down the road. It has also been used presently. There's been some Method 301 studies comparing Method 301, which is the direct PTR, to what's called EPA Method 18, which is a reference method for GCs that are coupled to various detectors. And occasionally we'll put the GC in front of the PTR so that we can separate the compounds, and then the PTR actually does the analysis. However, we can get better detection limits if we actually eliminate the GC and go direct. Next slide, please. All right, so this is, I think, very impressive data here from this case study, and let's take a look at this PTR data. So what we did here was we actually, we took the van and we drove it from Austin, Texas to the city of Houston, Texas at approximately 50 to 55 miles per hour at a reading of about 1 data point per second, which gives us a reading of approximately every 80 feet as we travel down the road. And what we're doing here is we're tracing the BTEX compounds simultaneously as we drive. So when I left Austin, Texas, you can see I was stuck in rush hour traffic. Sitting in bumper to bumper rush hour traffic, you can see the BTEX levels start to creep up as the traffic increases. But as soon as I start moving again and move outside the city, the BTEX compounds quickly fall until we get outside the city of Houston. And as we enter the city of Houston, we're actually finding many different hotspots. These are locations that have elevated concentrations of either one of those BTEX compounds or all of the BTEX compounds. And each color on these Gaussian peaks here really represents a different target compound. You can see that as we zoom in, you can see various hotspots that develop, and we can do this for multiple compounds. Let's drill down a little deeper. Next slide, please. Okay, so if we drill down deeper into the data, now the platform allows you to zoom in, to pan, to tilt, to rotate around these peaks. And what they're telling you is that you're in fact picking up higher ambient concentrations of a particular target compound. And then it's very easy to quickly look around and see who might be the offender or where it's coming from. And then we can send in the LDAR teams to actually pinpoint the exact location of a leak. So this is the same as driving around a facility, say 10 times a day, or just sitting outside downwind from a facility and looking at the emissions. Now we're actually doing this in California for odor allocation studies to actually fingerprint each facility and then go farther downwind into a community that has odor complaints. And by using multivariate analysis, we can actually allocate the source of the emissions to the various industries that are that might be the suspected release of the odorous compounds. Next slide, please. Okay, this is another case study where we took the PTR and we drove it from Chicago, and we took it all the way down to a loading dock facility at a refinery in California. And here you can see that ambient air contains various levels of benzene, depending on whether you're driving by a gasoline station or you're sitting in rush hour traffic. But obviously you can see here on the graphs to the left that as soon as we enter the monitoring site, we're starting to pick up higher concentrations of the BTEX compounds. And remember, this can be hydrogen cyanide, this can be acrolein, it can be 1,3-butadiene, it can be 1,4-dioxane. It's up to you what compounds you really want to know, and then we can actually tune the instrument so that we're only looking at those compounds, because obviously there is some concern obviously about opening cans of worms outside of industries, and we don't want to do that. We just want to solve an industry's specific problem. When we do, we can then send in the LDAR teams, and then they can find and repair the issues at hand. Now, at the same location, about every hour or so, an 18-wheel tanker truck of ethanol would pull into the loading dock, would unload their load of ethanol into storage tanks. Even though there's vapor recovery units on those systems, every time they start to unload an ethanol tanker truck, we see a spike of ethanol, and we're located hundreds and hundreds of meters away from these facilities, but of course in a downwind location. And what we see here is that throughout the day, the source of ethanol emissions are actually increasing, and we attribute that primarily to the increase in the ambient temperature, which of course increases volatility. But also it could be because maybe the tanker truck drivers are just getting sloppier, or we're having a failure of a seal, or some other problem might be going on here. Next slide, please. Here's another case study where we actually drove through a metropolitan area. This happens to be downtown Chicago. And here we're looking for ethylene oxide. Now, ethylene oxide is a very, it's been all over the news lately. I'm sure you've read about it. We've done a lot of work in ethylene oxide. And here we're actually looking for sources or contributors of ethylene oxide that might be moving onto a facility or moving off a facility. And here we actually did a study, and here we found, you can see that peak on the graph on the upper left, we found a very high hit of ethylene oxide. And when we sent in the LDAR team to take a look at it or what it might possibly be, they did say there was a rail yard viaduct nearby, and a lot of ethylene oxide is actually moved around in railroad tanker cars. And so very likely there was either a spill or a tanker car that was leaking ethylene oxide in that location. Next slide, please. All right, here's another example of the reproducibility and how this technology can actually help a facility. Now here we're looking at both pre-COVID and post-COVID BTEX mapping in a Chicago area. And here you can see pre-COVID, obviously with a lot of traffic and business going on as usual, we have elevated levels of BTEX. But when 2.5 months later, after COVID hits, we go out and ride the exact same route, we can see that the ambient levels of these compounds have dropped significantly. Now we can still find hot spots, so that obviously doesn't mean that it's all gone, but it actually makes it easier to find those locations. Or what we can do is we can actually go upwind from a facility, and then we can find out what's moving onto a facility. It might be coming from your neighbor, it might be coming from a mile away. It's very important for a facility to know, especially when it comes down to benzene, whether or not that benzene is moving onto their facility, and then they're going to be blamed based upon their EPA Method 325B program. So this shows a way that a facility can generate its own data to see where they stand. We can locate hotspots, and then of course the LDAR team comes in and fixes whatever the problem is. Next slide, please. All right, very quickly, I'll talk about some other technologies that we use, and these are primarily open path technologies. Now, these are essentially more cost effective because we're not leaving the van sitting there for weeks at a time. If we want to do a longer term study, we'll actually put these out along the fence line. And a lot of these technologies can actually measure up to 1 kilometer in distance. So I'm going to quickly talk about these. Next slide, please. Now, again, if anyone has any questions about any of this technology, please feel free to reach out. I'd be happy to discuss it with you, its capabilities, its pros and cons, and of course, costing. Now, examples of some of these open path technologies, this is what some of this instrumentation looks like. Can be used in near road studies, can be used for finding leaks from landfills, might be a perforation in a landfill cover. It could be a volcanic plume, which that is actually a picture down in the lower middle from an 863 meter path length. We were measuring the volcanic plume. They can be put on panning heads so that you can share distances and you don't need as many instruments. These are used extensively right now in California refineries, which is required by the 1215 and 1180 rules in California, which requires an industry, a refinery, to be able to measure multiple path lengths around the facility to protect any downwind sensors from the downwind receptors from the facility. Next slide, please. Now, open path technologies, you have to be careful. You really have to know how this technology works. You have to know the assumptions. And so 2 important things I want to point out here. When we're using open path technologies, if you have just a one retroreflector, what usually happens is you send a signal from a telescope, it goes out to a retroreflector. That retroreflector bounces the beam back to the telescope where the analysis is done on a CPU based upon the spectra, calibration spectra, and some type of chemometric model. Now, this works very well, but the problem is, like such as California, they're using one retroreflector at a very long distance. So what happens there is that you're not, in fact, determining the extent of the plume or whether or not you've captured the entire plume. And that becomes very important if you really want to quantitate or determine some type of emission loading, or in fact, the most important number, which is the flux measurement, which is a mass per unit time moving across the fence line of your facility. So what we do is we use multiple retroreflectors, or we call them targets. And by putting them out at various distances and then sharing time between them, we can very accurately determine the extent of the plume, and of course then the highest concentration in the plume, which of course is going to affect downwind receptors. Next slide, please. All right, so how this is typically done is many times what's called the 1D fence line design setup, and this is in the OTM 10 and OTM 33A rules that are published by EPA, called Other Test Method 10 and 33. And so what we do is we use multiple targets, and by doing such, we can determine the extent of the plume. And then with the next slide, well, that's one way to do it. And then we use the triangulation software to determine where it's coming from. But another very powerful technique is called vertical radial plume mapping, VRPM. And what we do here is we put out multiple targets along the path lane, but then we also put them out at elevation. And that, therefore, you create a pie-shaped wedge. And by doing so, you can then determine the flux, or the mass per unit time passing through that cross-sectional area of your fence line, right? And that's how we basically determine very large area fluxes from very large sources. And it works very well. Next slide, please. All right, here's an example of how the triangulation system works with these various technologies. Is that the most accurate way of doing it is to do a transect or a perpendicular at two path lanes. And they don't have to be very long path lanes, a couple hundred meters, but it could be much larger if needed. And then by taking the transects of these two, the software platform will actually figure out where those sources of emissions are coming from. And here we actually did the tests. We ran the software triangulation program in various open path technology. And here those green dots are where the ethanol tanker trucks are actually unloading their product. That's the vapor recovery unit and the storage tanks. So you can see that the ethanol is in fact coming exactly from the area we would expect. But when we looked at alkanes, we actually saw that they were coming from the actual diesel tanker trucks themselves. So there were no leaks of alkanes coming from this facility. They were actually coming from the engine exhausts of the parked tanker trucks that were idling and waiting for their load to be unloaded. So very powerful, very sophisticated software and technologies. And of course, this aids the LDAR team in going in and addressing those issues very quickly. Next slide, please. All right, quickly want to mention that because Montrose plays with a lot of these types of technologies and we work with many different vendors, you have a lot of differences between the hardware and the software capabilities between vendors. Now, the hardware of OpenPath Technologies has really advanced over the last 10 years very significantly. However, the softwares have fallen a little behind and they are catching up. But obviously, when you have to make a monetary investment in software, they do tend to lag behind. So Montrose has developed its own software, which is a very sophisticated artificial intelligence, which uses an iterative process to very quickly, I'm talking hundreds of spectra in seconds, to very quickly reduce the detection limits of some of these vendor products. And it also eliminates the false alarms, both positive and negative false alarms, by up to 90%, depending on which vendor you're using. And we know all the vendors and we've worked with all the vendors, so we know which ones work, we know which ones need a little help, and we're very capable on deploying, servicing, and using these technologies. And you also get a validation, which shows up in the upper right-hand corner. So after all the data has been crunched and all the algorithm is performed, the customer will be sent a validation spectrum that shows very quickly whether or not this is in fact real or not. And here you can see the green line and the red line, which is the sample after all the interferences are subtracted out, very quickly say that yes, that is in fact orthoxylene. Right. Next slide, please. All right, very quickly, I'm going to mention drones because we are limited on time here. And drones are obviously a buzzword. You hear them a lot. They are gaining a lot of media coverage. You see a lot of the larger oil and gas customers using these types of technologies, mostly along pipelines to cover large distances. But we do employ them with the LDAR team, and we do have an LDAR group that runs drones. So we have a drone group also with our CTEH group. And what we do here is we can in fact either mount an OGI camera on a drone, or we'll actually mount what's called a tunable diode laser that's really tuned to the methane frequencies for absorption regions. And then that TDL actually shines down to the ground, and we use the backscatter off of the ground to pick up the signals of the TDL, and we can detect methane down to 1 part per million meter, which means at 1 meter away, we can see 1 ppm. 10 meters away, we can see 10 ppm detection. So this is a much more sensitive technique than the OGI, which is really designed to measure much larger plumes, which is why we also have incorporated these TDLs onto our OGI cameras in our LDAR programs, so that one user can go out there, find both the large leaks and also log the much smaller leaks so that they can be addressed later on. And this is much cost-effective technique. It's also used for finding abandoned wells or wells that might have been plowed under or covered up over the years. And of course, obviously with greenhouse gases and methane and other things, we want to address those too. Next slide, please. And I think we're going to sum it up here. So I'm going to turn it back over to Tanya, and thank you for your time.
Thank you, Pete. That was really great. So we've presented a lot of technologies here today and teams to support the identification of your emissions, but some of these programs may only be one time to resolve a specific issue or concern or an odor. But for long-term or real-time notifications, the collaboration of the teams will really be important to drive home the efficiency. We recommend developing a monitoring plan to outline the protocols, procedures, goals of the team, regulatory and client requirements, contacts and responsibilities, and finally using this plan as a training tool for the teams that are all involved. Well, this kind of wraps up what we have today. We hope that you all have, witnessed a systematic approach to reduce your costs and your risk, and introduce you to some new technologies that maybe you haven't heard of before, that either you can implement at the macro Fenceline level or at the micro Method 21 component level. I want to thank everyone for joining us here today, and we now welcome you to open it up for questions. You can use your chat to submit questions today. And if we are not able to get to your questions today, then we will be responding afterwards as well. I see a few questions have already started to come in. This one looks like it's directed at you, David, if you want to unmute. Do you see Fenceline monitoring programs expanding to other industries or other compounds besides benzene?
So Tanya, that's a really good question. Yes, I definitely do. These programs, the passive tube Fenceline monitoring is being incorporated into different facilities, consent decrees. It's also being considered by EPA for other industries. And it doesn't have to be benzene as it is of petroleum refineries. They're kind of looking to implement this in other industries based on the applicability of this technology. Also, Fenceline monitoring is required in the state of California in a more real-time basis. And based on kind of what I see, I think that the real-time monitoring is going to probably expand to other states as well.
Great, thank you. Pete, this one looks like it's for you. What if any of these technologies could be used to monitor H2S?
Yes, absolutely. We all of these technologies actually can, well, not all of them, but many of the different classes we have technology to measure H2S down to part per billion levels. Obviously, the TDLs are being used in California in the open path capacity, and sometimes they're being mixed with some extractive units, fluorescence, and other things. The PTR can easily measure the H2S down to extremely low levels, and of course, we would use, there's a new open path QCL that we are strategically partnered with, a company that is in fact has a very capable QCL that can do C1 through C5 plus. And then of course, the TDLs are generally used for the H2S compounds, but we can certainly do them.
Great. And I think this question's probably open to all three of us. So Pete, we'll let you start. But Fenceline programs were used as an example here of, when to go into one of these programs. What other reasons could cause a need for a program like this?
Well, a lot of the times we'll have complaints from community groups. Now, we tend to work for industry a lot, so sometimes there are conflicts of interest and we can't work with a NGO or something. But usually when there's odor complaints, irritation in a community, somebody makes a complaint, we'll be called to go out and do an investigation. And that's in fact what we're doing with AQMD in California, not against any industry, but more R&D to see if these techniques work, because they will employ them. But we'll go out there and we'll determine what those odorous compounds are, and then we can actually fingerprint a facility and determine whether a facility is at fault or in fact not at fault, right? Sometimes it's really, even marshland does contribute odorous compounds. And how do you separate, say, a marshland from a facility that's emitting odorous compounds? Who's to blame? So we employ tactics that we can support our customers in defending their facility.
Great, great. And David, do you have anything to add on that?
No, I think Pete covered pretty well. One of the things that he brought up was that in the NGOs and things like that, I think it's important to be armed with tools to understand fugitive emission profiles of your own facility and be able to defend yourself if that comes to pass.
Especially if you're in a high industrial area, right? I think that's kind of where I see it. We took this approach from the Fenceline macro going in, but from my perspective, LDAR, we're looking at the small components every day. When you start to see, patterns or issues coming, you can really take a step back and use these technologies to get the bigger picture. And I think that's why it's nice, because right now, Fenceline is used for, mainly refineries, but there's plenty of midstream and upstream clients that could use these technologies or these approaches, or even Fenceline, to incorporate into their programs and get that macro level.
Yeah, many times a facility. Oh, go ahead, Dave. I just want to quickly say, many times a facility just wants to know where they stand. And then if we do find something, they can quickly address it and put it to rest, right? And then periodically we can supplement LDAR programs too by occasionally coming out and making sure everything's just fine.
And to add on to what you said, Tanya, I think this is also applicable for chemical manufacturing, as there are some chemicals that the EPA has their eye on as well, some suspects for folks in low income areas, communities. So definitely is applicable across multiple industries.
Great. And, again, this kind of applies to maybe all of us, but maybe David, you want to take the first stab at it. What does communication in a program like this look like?
So I think that's kind of hard to say, but I think the approach that we would take, for a program like this is that a facility would have basically a single point of contact as like a Fenceline program manager, and they would kind of orchestrate the progression through these various stages. So you would have your routine program, you would have maybe a hit, and then there would be a collaboration internally, and we would involve the facility kind of along the way. They could be as involved in that process as they'd like, or kind of in the back. We would probably rely on them for some information that wouldn't be readily available to us about processes that may be going on the facility, or maintenance were not there. So it would just kind of operate, and we would progress through the stages, obviously with communication and present the various solutions and proposed progression through that cycle.
Great. I've gotten a few questions about this. This is you, Pete. How expensive are these technologies?
Sure, the golden question everybody wants to know. I think you'll really be surprised at the cost effectiveness of these technologies. Obviously, the longer they're deployed in the field, the more cost effective they are. It's really the mobilization, which is the highest cost. But even the PTR costs no more than a compliance field test. So it's not orders of magnitude above that. It's very reasonable, and of course we can design it around a budget too. So at least get the conversation going. We'll be happy to talk to you and give you competitive pricing.
Great. How do you determine which technology to use?
Who's that for?
Well, I think that's all of us, right? In my case, for the LDAR group, we look at what we're trying to do. If we're doing an investigative finding, then I think the OGI really is it's the best way to start. And we usually take that approach because you can scan first and quantify later, right? So for my technologies, that's where we start.
Yeah, I think the best analogy would be, look, if you have one technology, everything looks like a nail, right? And it's your hammer. Montrose employs multiple different technologies, have various levels of competency in terms of detection limits, reproducibility, whether it's compliance or reference available, right, to meet reference method capabilities. That might be a requirement, so that would dictate a particular technology. Obviously GC based, right? But many times, we can suggest a more simpler approach, right, that will solve your problem instead of, throwing an expensive piece of technology at you. But if it warrants a more technologically advanced technology, we have those, and we will basically sit down with you and tailor it to the target compounds of interest. And we'll talk about those pros and cons. We'll talk about, the pitfalls, what you have to look out for, and hopefully we can, we'll design a program that exactly meets your needs.
Great, and I think we have time for one more question. Do you foresee method 21 going away? You know, I think, you know, method 21 has just been around for a very long time now, and it's very effective. It's very specific, and I don't see it going away, but what I do see is it paired with more technologies. And as industry and the regulators get more comfortable with these various technologies, we can be more efficient and more cost effective by incorporating other technologies with the boots on the ground method 21. And I think it's a nice complementary service that supports the needs of the facilities and the communities. So I think that's all we have time for today. Again, we'll get back to you on other questions that have been submitted thus far, and feel free to reach out. Our contact information is on this last page here. And thank you so much, everyone, for joining us. We hope you enjoyed it.
Thank you.
Thank you.
Thanks again, Montrose Environmental, for a great presentation. Please visit them at montrose-env.com. The on-demand version of this presentation will be available in about 2 hours at bicwebinars.com. Feel free to watch it again and share with your colleagues. On behalf of BIC Magazine and Montrose Environmental, we thank you. Have a great day.